Good morning, one and all present here. Good morning. And good morning. So today I'm going to start my topic. I'll start my introduction. My name is Princeton Costa. I'm from class 11, and today I'm going to do topic of sine x graph. So I'm going to do the representation of the sine x graph and sine function. So this is the index which I'm going to be following, and I'm going to explain through this through chronological order. So this is introduction in history starting, and along with that questions and definition of sine x, shape and key features of the graph, transformations of sine x, applications of the sine graph, and real life examples, conclusion, acknowledgement, and references. Before we start anything onto something, I want to start the introduction. So maths is very beautiful language. So maths is used everywhere. Like in every subject, maths will be used for numbers or anything else. Maths is very important. So we can consider like a universal subject after like English. So it helps us to describe patterns, motion, and logic as well. So one of the most elegant and most useful patterns is a sine x graph, which is part of the trigonometry, and it's called a sine wave because of the wave, and it's represented by the equation y is equal to sine x, which I'll be explaining. So this curve is the foundation of the trigonometry and plays a vital role in this presentation. So I will explain how the graph works, its properties, and where we see it around us. So this is the history behind sine x graph. So it started in ancient India in 500 CE. So the word sine was actually called as jya, that means bowstring, by Aryabhatta. So Aryabhatta created the first sine tables for astronomy. So keep in mind, so sine x and some other trigonometric graphs were like used for mainly astronomy. After decades and centuries on, we get to know its purposes. So in the Greek astronomy, Hipparchus made a trigonometric table to track the stars and the patterns in the sky. So the birth of the graph was started by René Descartes in 1637. So he's the one who invented coordinate system, which is well known in maths in our textbooks. So later on, Leonhard Euler in 1748 defined sine mathematically. So like where it can be used in the graph and in exponentials as well. But I'll not go to exponential levels. But then the modern understanding was caused by Joseph Fourier, who is a mathematician who showed that all waves, so sine x waves have some sort of application with them. So it showed that like how we can use. So this became a foundation for where real life examples we use it today. Okay, I will ask the interactive question. What is the domain and range of the sine function? Is it A, B, C, or D? There's two options in MCQ. So which are the options here?
B option y belongs to minus 1 to 1.
Yes.
Solution of 1 minus 1 and 1 is one of the right answer. It implies the range of the sine function, and x equals to minus infinity to infinity.
Yeah, this is correct. A is the domain, B is the range. You're absolutely correct. So next, the definition of sine x. So the sine function relates an angle of right angled degree triangle. So before we do, we need to know what sine x is. Hariom, what is the measure of sine x?
Perpendicular by hypotenuse.
Opposite side by hypotenuse. Yeah, same. Okay, because I learned different. Okay, so y is equal to sine x is equal to opposite side of hypotenuse. That's correct. So x is the angle which usually we call in question is theta. So this is the angle which we will represent, and y is the sine value. Value it's minus 1, 0, or either one. These three options. So it's between that. So the sine function is periodic, meaning it repeats its value at regular intervals at 2 pi radians, 360 degrees. So this is the graph of y sin x with specified x axis values. I'm going to now plot the graph. Just for reference, I'm just using intervals of 30 degrees because it's easy to plot the values for that. Keep in mind it starts actually at 0.5 here. 0.5 starts minus it. So from there we can see a wave like this, wave pattern. So before we start, here it goes down by pi, this is 2 pi. Here is 30 degrees. It starts like this, and I have to just keep this is 0, and minus 1 is down here. Minus 1. So, like, what can we tell from this pattern? That we can say the sine wave is periodic function. Now I'm going to plot the values. Now here it's pi, 2 pi. Here it starts, see, from pi by 6 it starts, then pi by 3. Pi by 6 is 30 degrees. This is 60 degrees. So it goes to half over here. Forgot to mention it's half. So here it is 60 degrees. And after 60 we get 90 degrees. 90 degrees is at 1. Just to keep in mind. Then after that comes 120 degrees, then 150 degrees, then so on. So we can see that it reduces over time. It goes up and goes down. But you can see a pattern over there. 30 degrees, right over here, it starts at exactly like around 0. It starts, like, it's like the starting. You can say 60 degrees is at half. Next 90 degrees is at 1. 120 degrees is going less. Like root 3 by 2. I forgot to mention it's root 3 by 2 over here. That's equal to 0.8, and 150 degrees is half, like that, and goes down. Down it touches. Pi is 180 degrees. So that is 0. It goes down to 0. And again it continues like this. Like now I'm going to tell after pi, after 180 degrees comes 210 degrees, then 240 degrees, 270 degrees, then 270 degrees, then 300 degrees, and then so 270 times will be around down, that is minus 1, end of it. Here the 210 is minus half, 240 is minus root 3 by 2, and again it goes up. So you can see some pattern over here. As you can see, 2 pi, then 30. You can see pi plus like 180 plus 180 gives 2 pi, that's end over here. So 180, in terms of 180, gives us 0 degrees. But here 270 degrees are 90 degrees, right? So 90 plus 180 is minus, like 270. So minus 1. So 270 degrees minus 180 degrees is gives 90. So here we are seeing something odd. So here it's 1, and here it's minus 1. So you can see the pattern over there, the pattern. So this is 90 degrees, this is 270 degrees, and 2 pi. So main intervals of it, 90 degrees is the highest value. Then plus 90 goes lowest value. Like that. There's a pattern over there. You can see there is over here. Oh, this is just one period. Okay, so keep it in mind. So one cycle is one period. So this is how the plotting of the graph works. Like this, and it goes like this. So these are the values over here. What it signifies. So 0 is 0 degrees. So pi by 6 is half the value. Then pi by 4 is root 2 by 2. Then pi by 3 is root 3 by 2, minus 0.87. Then pi by 2, 1. Pi by 2 here is given 1 here. So then it starts going down again. Root 3 by 2, 1, and goes down until pi is 0. Then it goes even further down. 7 pi by 6 minus half. Then 5 pi by 4 minus 2 minus root 2 by 2. Then minus root 3 by 2, like that. And then suddenly it increases up. Just it increases. Once it goes down to the end, its end point is like 270 degrees minus 1. Then it again increases further on. Then 2 pi will give us 0.
I'm just saying that variance are important.
So next we have the shape and key features of the sine x graph. So the graph of y is equal to sine x. This is a smooth, continuous wave-like curve, like sine wave. So it repeats at regular intervals. It goes up and down. There's like where points. So it's the most fundamental periodic function in mathematics. So its shape. So the sine curve wave starts at the origin, 0 by 0 and 0. So later it goes to its maximum value, that is 1. It goes down after its maximum value is 1. Then it goes down to 0 degrees. Then again it goes further down, and its minimum again goes minus 1. then again it goes to 0, like that. So the amplitude is the maximum minimum values of sin x are +1 and -1. So hence the amplitude is 1. So the period. So sine function completes one full cycle when x is increases by 2 pi radians, that is 360 degrees. So that sin x graph, the value, it repeats every 2 pi. Once it goes to the 2 pi, again it continues and goes so on. Next, the zero crossings. The graph crosses the x-axis at x is equal to 0, pi, 2 pi, 3 pi. So it maintains the 0 degrees at pi and 2 pi, like that. 180 plus 180 plus 180, like that. So it occurs when x is equal to pi by 2, 5 pi by 2, 9 pi by 2. That those are the maximum points. As you can see, 90 degrees is plus 1. So positive 1. So minimum points, my points are going down, 270 degrees, -1. So that's one of the best examples I can do, -1. So this is symmetry over here. So the symmetric graph is sine minus x is equal to minus sine x. You understood, right? Like here sine x is 270 degrees, like that. So domain and range. The domain is all real numbers, minus infinity and infinity. So it keeps going on. Minus infinity means it goes down to negative value, then goes up, like that. Continues. The range is -1 and 1. So the range of the function is y to y epsilon r. So -1 is less than to equal to y is less than to equal to 1. So value of y lies between this -1 and 1, or it can also be -1 also, or it can be also 1 as well, depending on the way of the waves. So now the transformation of sin x. So basic sin x can change its shape or position depending on its equation. So its transformations are like usual, like it's common, like it goes up and down like this. So here we could see y is equal to a sin x, changes amplitude, its height changes, this is a sin x, it goes down like this, that time. So y is equal to sin bx. So period, frequency changes. That is applied to applications like car suspension. The graph is a bit smaller like this, which I'll show you. So y is equal to sin x plus c, shift vertically. Vertical shifts are there. Next, we have y is equal to sin x plus d. So shift horizontally. Horizontal shift will be there. It's like oscillations in the clock. So applications of the sine graph. So sound, music and all. For example, headphones, speakers, they use sound waves like hertz and all. They have to describe it through sound waves itself. So electricity, AC current when passing through. So the current and voltage may vary because of the sine waves over some time. It's like a pattern. Based on the pattern, it moves, like that. So light waves are also one of the best examples I can give. It oscillates sinusoidally in electric and magnetic fields. Magnetic fields, right? We have the radius and solenoids. Solenoids, we have the radius. So continuously the radius, like when the magnetic field. So there's like some patterns, intervals in it. So these intervals can be represented to sin x graph, the waves. Then engineering, mainly engineering is one of the best. It's like foundation for it. So studying vibrations in bridges, machines and vehicles, civil engineering as well. So tides, the rise and fall of tides follow sine-like motion, and medicine, ECG and EEG graphs. We've seen in hospitals, movies and all. Like we've seen the heart machines and all that check the pulse or even pulses and this one heartbeats of the patient. So the heartbeat of the patient, it goes up and down. It showed in a graph, ECG graph. So it shows a brain waves also can be seen. Now I want to ask you to take a look at this. Now can you take a look at this? So as you can see here, this is the car. So this is the best example I can give. So this car, we can see, observe its tires are going up and down. Why? Suspension. Now why, you may wonder, why did I use suspension as an example? I'll tell you now. So as you can see, this is how the suspension of the car works. It goes up and down and there are springs as well. So this is a caliper of the car. So that's also taken in. So they taken sin x waves as a consideration so that they can see the pattern of the car when it goes up and down. This is very useful because we can see how the suspension works. Because without suspension, the car would just bounce up and it would just bounce. So sin x graph is one of the best examples I can give for this. So I have told you already, like this has gone, see the pattern, the frequency, it has become smaller and smaller, like that. Then now I will reach to the conclusion. So the graph of sin x is much more than just a mathematical term. It's a symbol of rhythm and harmony found in universe. Meaning so many applications are there based on just a sin x graph. So many applications. We even don't know in the future how much applications will be taken because of the sin x graph. So its repeating patterns represent balance, motion, continuity, relativity, and so many physics applications as well. From sound to light to tires, car suspensions, and all. We've seen how the sine wave is much important in our day-to-day lives. So it connects mathematics, the natural world, proving that math purely describes itself. So it shows that pattern because sin x graph is purely just a pattern of waves continuously, but it shows the true nature of maths because maths also runs on logic and continuous waves. So I want to give my acknowledgement. So I would like to express my gratitude and as well as sincere gratitude towards my teacher Sujata ma'am, to my classmates to bear with my behavior when doing this, and this project has helped me understand the concept deeply. And principal ma'am, Vani ma'am, and administration ma'am, Swarna ma'am, and I would like to thank everyone, the school classmates for their constant support in keeping my behavior like you understood. So my preparation of this presentation. So these are the references which I've taken from. I've taken from NCERT Mathematics, Class 11, Chapter 3, Trigonometry, and Concepts of Physics from H.C. Verma, Volume 1. So Khan Academy as well for the graphs and trigonometric functions which you have seen here.